So that increases the load a little bit because the encoding um, to YouTube takes up a little bit processing power. But I figure out how to use my GPU to do that part, so it's not actually taxing the main processor as much as before. So that should help a little bit. And I also figure out how to enable video decoding, hardware video decoding in Discord. So that also helps a little bit once I start to stream. So let's see. Yep. Okay. All right. We are about 2 minutes out from the beginning of today's class. So in today's class, I'm going to go over the practice exam. And let me go find the practice exam first. There we go. Alright, so the practice exam is here. So I'm not really sure how much time I would have left, after the practice exam is done. But I do have a lab planned for today, because if I don't, we might not have enough time to finish all the topics that we need to go over. So there's that. Alright. And I have been grading. I'm not forgetting to grade exam 1. There are some submissions that are very time consuming to grade. There are these ones where it's not empty, so there's some reasoning, and there's some bits, zeros and ones, but there's no logical connection between the zeros and ones. So I have to kind of go through the logic and go like, okay, this doesn't seem to make sense. There's no explanation of how this is, and so following those kinds of non-logic, is extremely time-consuming in me, because I have to kind of follow that and go like, does that make sense? No, it doesn't make sense. Then what should we do about this, right? What am I going to do about the values that depend on the reasoning that is not logical? So there's a lot of stuff that I need to do, and it gets extremely slow grading those particular types of answers. Now, on the other hand, I also get answers that are 100% correct and well explained, super easy to grade. Just check, 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 and we're done. I also get answers that are missing or entirely wrong. That's also easy. Just, oh, okay, no answer here. The answer doesn't make any sense. So, so how much time it takes to grade each exam really depends on, what is turned in, unfortunately. All right. So let's take a look at the time. It is time to start. So the first thing we're going to do is to start with the practice exam. So this particular practice exam was from last fall. This is from last fall. And the first question is the analysis of a circuit that is given to you. And in this case, the pins are labeled similarly, to in the discussion in class, but they may not be the case. Okay, so you don't want to rely on that fact. In fact, I can give you a circuit that you may not have seen before, but it is related to a circuit that we did talk about in class. So keep that in mind as well. Alright, so let's go ahead and analyze this circuit, and I will also give you the answer along the way of what is expected as the answer. I'm looking for the text editor, so I'm gonna have to make a new one. There we go. Alright, so the question is asking from only the given state of the input pins document the output of all the gates and SR latches, and you need to analyze all the state changes within the circuit. So I'm gonna tell you guys right away, you can put this into LogicSim. I would not consider that cheating at all. Okay, you can put this circuit into LogicSim, but if you just report what LogicSim says about the output and the inputs, that would not be sufficient to get a good grade, because there are hidden states in between that Logisim cannot reveal to you. So let's go ahead and take a look at what that means. Alright, so the first thing we want to do is to start with, so if you look through the question, we are just basically changing the input pins, one at a time. Sometimes it can be two, both bits are being changed at the same time. It doesn't really matter, because I want you to help me analyze how the change of the input pins is, how that change is propagated throughout the circuit. So you'll have to give me the reasoning, of how that change spreads throughout the circuit. So let me go ahead and describe that first. And this is the PDF that I distributed yesterday. So if you go back to the text channel from yesterday, there's a link, there's actually a file attachment that you can download. Alright, so the first part is, okay, so I kind of need to keep this diagram here so that we can see it. So we start off with EN being 0 and D being 0. Okay, so let's see what gates are going to be impacted or changed by these two pins having known values. So you basically assume you have no idea what the rest of the circuit is doing, and this is the first known change to the circuit at this point of time. So that means you have no idea what the SR latch is outputting at this point, what state it is in, and the same goes for the NAND gates. Now when we have two NAND gates, N1 is a NAND gate. When at least one input of the NAND gate is a 0, the output is going to be 1. So now we can say N1.out equals 1 because at least one of its inputs is a 0. And I'm going to use pin D to basically make it more complete, because I want to know okay, so which input is a 0? Well, at least the one that's connected to input pin D. And the same argument can be said about the second N2, the second NAND gate. So we can now say N2.out is 1 because at least one of its inputs is a 0, and in this case it is pin EN. Alright, so that's the first change, and because N1.out connects to SR.S and N2.out connects to SR.R, now we get to decide what the SR latch is going to do. So now we can say SR.S is a 1 because it connects to N1.out. SR.R is 1 because it connects to N2.out. Alright, so there's something in the text message. Oh, okay. I can always turn off the face cam too. So there we go. And also, I think the writing is a little bit longer. There we go. Alright. So now we know both input pins of the SR latch are 1s, which means we know the SR latch is preserving its current state, but we do not know what its current state is. So all we can say is the current state of the SR latch is preserved, but we have no idea what it is. Okay, so you can even say, okay, if you want to, you can say SR.Q and SR.NQ are currently unknown, which also means pin Q and NQ are also unknown. Okay, so you can say pin Q and pin NQ are unknown. There we go. So that completes the first state, which is having both input pins being 0s. And now we move on to the next one, which is EN is 1, D is 1. Okay, so now we go to EN being 0, maintaining its state, and then D is 1. So the only one that is changed is D, the data pin. And then I go back to the earlier diagram because I need to follow up. I need to follow the diagram to find out what type of change is going to propagate. So at this point, the D is connected to N1. So D becoming 1 is certainly going to impact N1. and then En is still 0, so we have to look at what N1 is going to do because of the change of D. D also connects to N2 through a negation, through a NOT gate. So a change of D can potentially also impact N2. So we have to analyze those two NAND gates again. So we look at N1 first, and we say N1.out is still 1 because at least one of its inputs is a 0, and this time we can say it's pin En, which was 0 before, and now it is still 0. So that's why N1.out is not going to change. N2.out is, let's take a look. So N2 also has one of its input connected to En, and that was explained earlier. Okay, so that would still be 1 because at least one of its inputs is a 0, which is also pin En. And now we can say no further changes in the circuit, because if N1 and N2 are continuing to output 1 compared to what it was before, that means the SR latch is not going to change, so there's no need to mention that the SR latch is not experiencing any changes because both of its input pins are preserved at this point. Let's track down the third state. So the third state is reversing the En and the D at the same time. So we want to see what's going to happen there. So En is now a 1, D is going to be a 0. So when I get back to the circuit diagram, now we have to kind of look at how this circuit is going to respond to both of the pins being changed at the same time. Now both of these pins, connect to N1 and N2. One is through a NOT gate, so technically they are still, connected to N1 and N2 almost directly. So now we look at N1.out and we try to determine what it's going to do. In this case, because En is now a 1, so we know the second input of N1 is going to be a 1, but D is a 0. So N1 is still experiencing at least one of its input pins being a 0, so it's still going to be outputting a 1. So we can say because at least one of its inputs is a 0, and this time it is pin D. Now we look at N2. So N2 is in a little bit of a different situation because D is a 0, so but it is negated first before it is going into the second input pin of N2. And then En is a 1, so that means both inputs of N2 are 1s. So we say N2.out is 1 because both inputs are 1s. And to explain that, one is pin D itself, and the other one is the negation of En. So both of those are giving N2 a, oh, right, okay, it's outputting a 0, not a 1. That's right, okay. I said 0, but then I wrote down 1. Okay, so now we have a change because N1.out is a 1, so SR.S is still reading a 1, but SR.R is now reading a 0. So now we say SR.R is now a 0 because it connects to N2.out. And as a result of that, we can now know what the SR latch is going to do. And we can say as a result, we should also mention that SR.S is 1 because it connects to N1.out. So as a result, the SR latch is going to change its state. So now we know exactly what the output is going to be for the SR latch SR. So now we can say SR.Q is going to be a 0, and SR.NQ is going to be a 1. And then we also can conclude that output pin Q equals to 0, output pin NQ is going to be a 1. So that would be the third state. And we are going to move on to the last, or the fourth state. So the fourth state is to have both input pins being 1s. So scrolling back to the picture, and we say En is 1, D is also 1. So in this case, we have to, so the only change is D. So whatever D connects to, we have to reanalyze. And well, D connects to N1, it also connects to the NOT gate that eventually will also change N2. So we have to reanalyze those two gates first. So N1.out is going to be, let's check. En is a 1, D is also a 1, so both of the inputs are 1s. So that means N1.out is going to be a 0 because both inputs are 1s. And that would be D and also En. And so that's 1. And now we need to look at, so instead of looking at this and continuing into the SR latch, we are going to look at the other NAND gate first, because both of these NAND gates are quote unquote at the same level. For the previous one, isn't it supposed to be pin En and not pin D for N2.out equal to 0? It's D for, oh, it's negation of D, that's right. It's not D and En. There we go. Because En is not negated. I negated the wrong one. Thank you. Good catch. Good catch. Alright, so now we move on to, right. So now we look at N2. So N2 is seeing a 1 coming from En, but it's seeing a 0 coming in from the negation of D. So as a result, N2.out, N2.out is now a 1 because at least one input pin is a 0, and that would be not D. Okay, because the second input pin of N2 connects to the NOT gate, and the input of the NOT gate connects to pin D, and D is a 1 in this case. The negation of D is going to be a 0, and if at least one input of N2 is a 0, the output is going to be a 1. So that means from the perspective of the SR latch, both inputs have changed. So now we have to look at the SR latch, and SR.S is now a 0 because it connects to N1.out. SR.R is a 1 because it connects to N2.out. As a result, because we now have the S input pin being a 0 and the R input pin being a 1, so as a result, SR.Q is now a 1 and SR.NQ is now a 0. And then output pin Q is now a 1, output pin NQ is now a 0. So that would be the kind of answer that I expect from a question like question 1. So it has to be step by step, and it has to kind of fully explain why the output of a particular gate or device is the state that it is. All right, I'm not seeing any questions in the text channel, so we're going to move on to the second question. So the second question is, in this question, you're given the following pre-dissected microcode slice. So let me first explain what the terms are referring to. Pre-dissected means, it is already bundled into these names, and these names do correspond to the tunnels in the processor design. So if you open up processor 0004 in Logisim, these names are the same names as in the tunnels. And a microcode slice is a location in the ROM of the processor. That's basically what I would call a microcode slice. So that's already decoded for you. So you don't have to basically look at 25 or 26 bits and have to kind of dissect it, and break it up and know which one goes where. It is already done for you. So the question says, first, identify the components that is going to be updated. This includes all the registers as well as RAM. For each identified component, explain why you think it is going to be updated. Trace your reasoning to the bits from the data port of ROM. You may refer to these using the names of the pre-dissected microcode, basically the names of the tunnels. Use the following area to answer this part of the question. All right, so let's find out what that means. ROM bracket 0 refers to bit 0 of the output of ROM. So to explain the answer of this question, I think it is going to be helpful if we just take a look at the processor itself. So let's do that. And let me see. Okay. Alright, so here's the diagram, and this is, oops, not that. Let me go find the question. The question is in the browser. There we go. Alright, so we want to look at bit 0 of the output of ROM and see where it connects to. And let's take a look. So here's bit 0 of the ROM, and where it connects to is the enable pin of the instruction register. So the instruction register is one of the registers to be updated in this case. So I'm gonna write that down in this text file here. So for question number 2, for the first part, we identify that the instruction register is going to be updated because ROM bracket 0 connects to the enable pin of the instruction register. Yes, I know you cannot see that part. I'm gonna break the line so it's easier for you to see. There we go. Okay, so that's one. Now we go back to the question. There we go. RAM cell is a 1. Okay. Now, if RAM cell is a 1, you know the RAM is being utilized, but we may not be updating it because when we look at RAM load, it is a 1 also. That means we are reading from RAM. So we are not going to say RAM is going to be updated because we are reading from RAM, we are not changing it. RIMux is a 1 by itself, doesn't really say anything about any register being updated. RIEN is a 0. That means none of the registers in the register bank is going to be updated. That's good. RI cell being 3 doesn't really make any difference because none of the registers in the register bank is getting updated. RO0EN is a 0. So that means register output 0 is not enabled. Once again, we are not, that doesn't indicate the update of anything. Register output 0 select is a 1. That simply means that we are selecting register B in the register bank to connect to register output 0, which is actually disabled, so it doesn't really do anything useful to us. Our register output 0 demux is a 3. That doesn't really matter because we are not outputting anything. So that the multiplexer is not really gonna impact anything, or it doesn't help to answer this part of the question. Register output 1 select is a 3. Register output 1 demux is a 0. Once again, it is not indicating anything to be updated. ALUEN is a 0, so the ALU is not enabled. It's not going to do any type of calculation, which basically means the op is not going to be really useful because even though we specify an operation, it's not going to happen. There's no input to process in that case. Okay, so I got a question do we have to explain why it is not updated? No, you do not. So you only have to explain why something is updated. Address mux being one, it's just switching between the two sources of what can be connected to the address port of RAM. So by itself, it also doesn't indicating what is going to be updated. PC mux mux is a 7 that can steer what we use to update the program counter, but by itself it doesn't indicate that the program counter is going to be updated. But PCEN being a 1 indicates that the program counter is going to be updated. So now we also have to write that down. Okay, so we say the program counter, and you can use the abbreviation. PC is going to be updated because PCEN connects to the enable of the PC, which is a register. And then we look at ROM24, which is bit 24 of the output of the ROM component. And this is it, okay? And let's see where it is going. It's going to the select of this multiplexer. So by itself, it also doesn't really tell us what is going to be updated. So we are now done with the first part of the question. So the instruction register and the program counter are both going to be updated. Getting back to the question, now we get to the second part. Next, identify how these components are updated. For each component that is going to be updated, identify how it is going to be updated. Using column C of the opcode table is a good idea of what this part would look like. So that's the register transfer language. You basically just use C assignment statements to indicate what is being used to update what, and explain why you think this is how it is going to be updated. So you have to use the multiplexers, demultiplexers, and other components to determine how things are being connected at this point. Alright, so let's go ahead and find out how that is going to be explained. Should we know something about the clock in this question? So that's a very good question. You can assume the clock is at a low state and we are about to have a transition to the high state. So in other words, clock is currently a 0 and we are about to have a rising edge transition. There we go. So that's a very, very good question, because on the falling edge, only the microcode pointer is going to be updated. So that's a very, very good question. Alright, so let's get back to the circuit diagram. Alright, so what we know now is the program counter, this guy here, is going to be updated. We also know that the instruction register is also going to be updated. The question is, how are they going to be updated? Okay, so we have to track now basically how the input of both of these are connected. So for the instruction register, it is actually the easy one to explain because it connects straight to the data port of RAM. So we know whatever we are addressing in RAM is going to be used to update the instruction register. So the next question now is what is being used to address the byte that is going to be used to update the instruction register. So for that, we have to track down the A port, and it goes into this multiplexer. So now we have to look up what the value of address mux is. So let's check that, because I cannot remember. That's why I have to come back here to check. Alright, so according to this, address mux, which is here, is a 1. Alright, so if address mux is a 1, that means input 1 connects to the output. So now we have to track this down, and it goes to the program counter. So that means the program counter is being used to address RAM, and whatever content is at that location, whatever is at the location that the program counter is pointing to, is used to update the instruction register. So for the answer to this part, to part 2, we basically say instruction register is whatever the program counter connects to, because RAM is being read and addr mux being 1 means the program counter connects to the you can always use the short form, kind of like object-oriented programming. So you can basically use ram.a to identify a port of RAM. Alright, so that answers one part of the question. The second part of the question is, we know the program counter is getting updated too. The question is, how is it getting updated? So we start with the D part of the program counter. If it's coming from the multiplexer, and this multiplexer is using PCMux. And PCMux is this tunnel over here. So now the question is, how are we setting PCMux? Because PCMux is going to help this multiplexer to select one of its input to connect to what we see as PCMux here. So switching to the question. There we go. We look at PCMux in this case. PCMux is a 7. So switching back to the circuit, it's using input 7, which is a constant of 1, to feed to PCMux. So PCMux is a 1. So I might want to just kind of write this down. So we say PCMux is a 1 because PCMux is a 7. And then PCMux in return is used to control the multiplexer that is feeding the program counter directly. So we know PCMux is a 1, which means input 1 is being used. So it would be this wire. But now it's coming from the output of another multiplexer, and in this case the other multiplexer needs to use PCMux, which we know is a 1. It's also using the negation. This little bubble here means it is negated before it is fed into the AND gate. It is coming from RO0EN, register output 0 enable, and I remember that is a 0. Okay, so a 0 negated is a 1, so that means this AND gate is going to be outputting a 1. Okay, so in the answer, we're going to mention that. So we'll say, PCMux is a 1, and register output 0 EN is a 0. So that means PCMux and the negation of register output 0 EN is going to be a 1. Alright, so if that is a 1, we go back to the circuit diagram. So if this is a 1, that means input 1 of this multiplexer connects to its output, and we locate that and go like, whoa, it is the same thing as what is feeding the instruction register. Well, that's actually perfectly okay. So now we can now say, PC is updated by whatever it is pointing to. So PC equals to the asterisk of PC because it is simply dereferencing first, get to the RAM location, get the content, use that content to update itself. That's what this operation is going to do. So that answers the second part of the question. Now we are getting to the third part. So the third part of the question says, does this microcode slice remind you of an existing instruction? Note that the dissected microcode slice of this question may change some additional registers, but as long as it does not interfere or prevent the processor from functioning, it is acceptable. This dissected microcode slice of the dissected microcode slice of this question overlaps with the function of at least one existing instruction as described in the opcode table. So I am trying to give you a lot of hints, okay? Because, maybe the opcode table as a spreadsheet is going to help, right? Find the instruction that overlaps the most with the given microcode slice of this question and determine the exact and specific mnemonic of this instruction. For example, CMPDA, because with certain opcodes, you have to specify the registers. Some other ones you do not use registers, so that you don't have the variations to worry about in those cases. Alright, so now we go to the opcode table. And now I don't even have to look at the opcode table because I have had memorized most of the content of the opcode table. But if you need to look up the opcode table, here it is. It might be helpful to print this out prior, or keep a local copy so that it's handy, it's easy for you to access. Paper may actually be helpful because your screen is only so big. Okay, I have a 4K monitor and it's only so big, but if you have paper, you can kind of flip through the paper, the pages a little bit more, a little bit more efficiently, especially if you use post-its or other ways to highlight and index your pages. But that's up to you. Okay, whether you want to do this electronically or whether you want to do this using paper, that's entirely up to you. So when you look up column C, you try to identify something that looks like what we have in the question, in the answer so far, and guess what? That seems to look almost exactly the same, except this one has extra parentheses that are not really doing anything useful. So there we go. We have the answer. We have a JMPI instruction. So now we go to the third part of the question and answer that and say JMPI. Wait, hold on a second, because I think the question asked about the opcode and not the mnemonic. Let me double check and be sure about that. Now it gets a little difficult because it's harder for me to find the right tab. Let's see. There we go. All right. So let me close that. All right. So this one is asking. Okay, this one is just asking about the mnemonic. So JMPI is the correct answer, because that's the mnemonic. And then the last part is to ask about the hexadecimal opcode corresponding to the mnemonic. And in this case, I believe it is 40, because 0100 is a 4 and then 0000 is a 0 in hexadecimal. And that is what the question is asking, is in hexadecimal as an opcode. So that would be 40. And to emphasize this is hexadecimal, I would use 0x40 just so that there's no confusion that I'm talking about 40. It is not 40, it is 40 in hexadecimal. All right, so moving on to question number 3. So question number 3 says, let's start with the value in base 10. It's v equals to 9.875. In the conversion of this value to a double precision floating point number bit pattern, a mistake was made, and the implicit 1 point part of the mantissa was actually included in what should have been just the fractional part of the mantissa in a double bit pattern. So this double here is the abbreviation of double precision floating point number bit pattern. The rest of the conversion was correct. Due to this mistake, what is the actual value represented by the erroneous double bit pattern? Use the following area to answer this question. Your answer should demonstrate your understanding, knowledge, and problem-solving skills of double precision floating point numbers. As such, correct final answers without proper intermediate steps would not get any points. Okay, so let's go ahead and approach this one. So now we have Q3. So with Q3, we first have to kind of find out what the erroneous representation is going to be. So we have to do the conversion just like as usual. So let me see. Okay, I can just copy the value. So value is 9.875 in this case. All right, so now we can do the auto conversion. So the first thing is we need to represent 9.875 as a bit pattern. So we can now break it down. 9.875 is 8 plus 1 plus 0.5 plus 0.25 plus 0.125. Those are all in base 10. And now we look at this and go like, what is 8? 8 is 2 to the power of 3. 1 is 2 to the power of 0. 0.5 is 2 to the power of negative 1. 0.25 is 2 to the power of negative 2. And finally, 0.125 is 2 to the power of negative 3. Knowing that, now we do the actual conversion, because 2 to the power of 3 is 1000. The number of zeros indicates the power of 2 when the power of 2 is non-negative. So we have 1, 0, 0, 0 in base 2, and then the next one is just 0. So that's 1 in base 2. And then the next one is 0.1 in base 2, because the number of position after the point is how negative the power is. That is regardless of the base. And we also have 0.01 in base 2. That is 2 to the power of negative 2. And then finally we have 0.001 in base 2, because that is our 2 to the power of negative 3. And once we do the addition, we have 1001.111 in base 2. So we have just converted a base 10 representation of a value into the base 2 representation of the same value. So we look at this value and go like, but that's not that's not in double precision floating point number. We are not expressing the value using a 2 exponent of 2 and then the normalized mantissa and so on and so forth. So now we have to do the actual conversion. So now we say 1001.111 in base 2 is so I'm going to combine a few steps into one, and you can do the same. So we can say this is 1.001 and then 111 in base 2. But then we also have to remember to multiply by 2 to the power of 3, because the number of times we shift the point to the left hand side, every time we do that, every time we shift the point to the left once, it is dividing the mantissa by 2. So we have to compensate by multiplying the modified mantissa by 2 so that we preserve the same value. Because we did it 3 times, so now we have to multiply by 2 to the power of 3. So now we basically say, so now we know what the representation should look like. So E is E2, the biased. Okay, so let me just be clear here. The biased exponent is the actual exponent, which is 3 plus 1023. That is part of the specification of the double precision floating point number. And that turns out to be 1026. That is in base 10, which is 1024 plus 2, which is 2 to the power of 10 plus 2 to the power of 1, which is then 1 followed by 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, plus in base 2, plus 1 0 in base 2. So you just basically look at this and go like, okay, let's turn this into an actual bit pattern. So we have basically all of these. The second to the last 0 is a 1, and then the last one is going to be a 0. So that is the biased exponent. The sign, okay, so let me go all the way back. The sign is a 0 because the value is non-negative. Alright, so now we have all the bits and pieces. Okay, so the bit pattern is first we start with the 0 for the sign bit, and then followed by the 11 digits for the biased exponent. So I'm just going to do a copy and paste here. And now we have the actual bit pattern of the mantissa. But remember, the question said, the person doing the conversion made a mistake. So the 1 point is actually represented in the bit pattern. So that means we now have 1 0 0 1 1 1 1, all of these bits. So because normally we do not represent this 1 here, and we only use the fractional part of the mantissa, which would be only these bits. But because of the mistake being made, that 1 is actually part of the bit pattern here. And the rest are all zeros. Okay, so we look at this pattern, and we ask, okay, let me go back to the question and make sure I'm not missing anything. Not that. Right here. Okay. So use the following area to answer this question. Your answer should demonstrate understanding. Okay, so it doesn't really quite ask for the hexadecimal representation of this thing here. Okay, so using the correct interpretation, this bit pattern represents the following value. Okay, so the value being represented, you can actually look this up in Wikipedia, the equation to find the represented value given a particular bit pattern of a double precision floating point number. You can look it up in Wikipedia. In fact, my module actually links to Wikipedia. Okay, so we say this is 1, which is the sign, times 2 to the power of, now that has not changed, okay, because this is the biased exponent, but the actual exponent is going to be whatever this value is unsigned minus 1023. So you can basically just repeat, what we have, which is 1026 minus 1023. That would be the exponent of the 2, and then multiplied by, now in the correct interpretation, the 1 point is not a part of the represented fractional of the mantissa. So we are going to take all of these as the fractional part of the mantissa. So that would make it 1001111 here in base 2. And now we ask, okay, what is that actually representing, right? So it's to simplify, we can say, this portion. Okay, let me indicate which portion. This entire portion is just 8. Okay, that's fairly easy. And then the other portion is to interpret a binary number that has a decimal point. So this would be 1 plus 1 divided by 2. There's no 1 divided by 4 or 8. The next one is 1 divided by 16, and then 1 divided by 32, and then 1 divided by 64, and then 1 divided by 128. So if you get to this point, okay, and you say, but I don't have a calculator and I'm running out of time, guess what? I'll count it as 100% correct, because what is left to do is really just punching this into a calculator to find the exact value, which is not exactly difficult to do. Need parentheses. Oh yes, that is correct. We need parentheses from here all the way to here. Thank you. That is correct. We do need parentheses. All right, so that would be the answer of question number 3. All right, well, that's it. There are only 3 questions in fall 2020. Any questions? So it would appear, oh, here comes a question. Oh, by the way, how's the video coming along today? How's the audio and also the screen sharing coming along today? Yeah, I think so. I would think so, because I did I did a few things to optimize it. All right. I was trying to see if there are any questions about the practice exam too. I think Eric was typing something earlier, but I don't see the actual post in the text channel. Oh, okay. We are continuing. Okay, very good. Oh, okay. I don't. Unfortunately, I don't, and it is very difficult to make one, because the design that I have at this point, it became like this because it changed. It changed a little bit. I had to add some more circuit, along the way. So the use of the tunnel was to make it easier to add a new component without having to cross the wires, everywhere. But there are still a lot of wires that goes everywhere. Like the highlighted wire right here, that just goes to a lot of places. So So unfortunately, no, I do not have a less spatially dense representation of the processor. Um, yeah, so you kind of have to just kind of remember, be a little bit more familiarized with the processor, and hopefully that will help out. Oh, to print out and to write notes on. Okay, there might be ways to do that. Um, I'm thinking about overlay, because you can use speech bubbles, just kind of overlay on top of the whole thing. Um, oh, okay. So I'm trying to see if that is going to help, because what you can do is to print out the overall design on multiple pages, and then you use scotch tape to tape those together. So now you have a larger physical piece of map of the whole thing. So maybe that can help. Yeah, you can use Logisim during the test. That's one thing, the online version of this test allows you to do is you can use the tool. So that means you can click on a wire and find out, where it goes. I think that should really help in terms of figuring out the connectivity between the components. The other thing is you can also color code these connections. Now it does involve a little bit of work on your part because you're gonna have to convert this diagram into a PNG or some kind of image format, and then you basically can use the GIMP or Photoshop, or whatever tool you want to use, and change the colors of some of the more important wires so that you can tell where it goes just by following the color and not having to visually follow the lines. So you guys can decide what works best for you. Okay, this is the one design that I have been using all of these years, so I have the advantage of being more familiar with the design. But since this map is going to be useful, and oh, don't forget, okay, do not forget about the ALU, because you might need to know what is inside the ALU for some of the questions, and also inside the register bank. So if you think having everything pre-printed and annotated and color coded is going to help, make sure that you do it to all three: the overall design, the overall logic design, the logic design of the ALU, and also the logic design of the register bank. So you might want to do all three. Yep. Make sure that you have those all readily available in exam 2, which is next Monday, by the way. Okay, so I don't see any questions right now. Let's go ahead and take roll. And I think I'm being predictable, in terms of when to take roll. I think that should help a little bit. Okay, so here's roll taking for today. And I'm gonna disclose the word, but I'm gonna specify the time first. So I'll give you guys up to 26, 6:26 to answer these questions. This one single question, I should say. So it is July 14th, 6:26 p.m. And I just copy and paste, save and publish. Alright, so the word to take roll is frame, Frame, frame. So just copy and paste it into the roll taking activity, and we are done with that. Alright, so there's a question about how many questions will be on the exam, on exam 2, and are we going to have the same format like last exam? I'm going to guess around 3 to 4 questions, but the scope is entirely different compared to the first exam. So the first exam really is testing how well people understand addition or subtraction, and also comparison, how those flags are set. So basically, in order for me to evaluate that, I use the Sudoku format, so that people have to start with the known bits and then use the relationship between the bits in binary addition and subtraction to figure out the rest of the bits. So that is why I chose the format for exam 1. Exam 2 is a little bit different because the scope is wider. It involves the microcode of the processor, basically, how the ROM component controls everything else in the processor. That's question number 2. Question number 1 has to do with the analysis of the change inside a memory device. So you might want to review, all of the memory devices and make sure you understand how they work. So that would include the SR latch, the level sensitive D flip flop, the edge sensitive D flip flop, and then also the level and edge sensitive D flip flop. So all of those, that's another topic that I want to test. And then finally, we have the double precision floating point number that I also want to test. So that's why we are going to have multiple questions, at least 3, because one question can only cover one of those areas. So the format is not going to be the same, where you would see, okay, the first 3 questions, is considered, one group, the next 5 is another group, and then the next 8 is yet another group, and then they are ranked by difficulty. That it's not going to be like that. Okay, it's just going to be a certain number of questions, and they all add up to the 100% of the question. So you have to answer every single question correctly to get 100% in this test. All right. Not seeing any questions or anyone typing. So I'm going to move on. So to move on, we are now going to talk about subroutines and how we can return values in a subroutine. So we'll start with something that is familiar to us. I'm just looking for the Logisim window because I want to close that first. Okay, so this is one. I want to close it. And oh, by the way, I also started a new text channel for River Spider. River Spider is really just the code name of the script. Where you can use it to, so you can combine assembling, simulating, and also trace analyzing into one single simple command called submit.sh. Okay. But to configure that, okay, to make that work for you, you're going to have to follow some steps. So if you go to the text channel right below, I'm thinking it's right below the general text channel, or right below the, oh, it's right below the off topic, by the way. It's right below the off topic text channel. So if you go there, you will find the zip file that you're going to need, and also a video to show you how to customize the spreadsheet to work for you. It's not simple, but it's also not necessary. Okay, if you do that, you might shave some time in terms of debugging your code. If you don't do that, you can still do everything manually, which is basically what people, including myself, have been doing for years. Okay, so yeah, it's nice to have, but it's not necessary. All right, so getting back to the new topic, right? So the new topic has to do with return value. So let me just use return value.c and then return value dot ttpasm, and use a big dash uppercase O to split vertically. All right, so we'll deal with the C code first. I always want to do a pound include stdint.h because this way I can specify the type of integers based on the width. So now we have a uint8 underscore t, an 8-bit unsigned integer as a function. I'm going to call f again. And this time it only returns a constant. Okay, so we'll say it returns a value of 4. We'll use a global variable because so far we have already introduced the idea of a global variable, which is a whole lot easier to deal with compared to local variables. And then in main, we are going to have a return 0 to mark the end of main, and then we'll indicate x equals to the return value of the call to function f, like that. All right, so looking at the C code, I think all of us should know what it's going to do, right? Because it's just going to call f returns a value of 4. That return value in return will be used to update global variable x, and the program is done. So now we want to look at the assembly language implementation. So let me switch to this side. So we're going to start with no op again, because if you want to trace this code, having no op, you need the first no op instruction. And because we have subroutines, we are going to have to initialize the stack pointer. And this time I'm going to use another way to initialize the stack pointer. Instead of using LDI D0, I'm going to use subdd. Because if you think about it, subdd is subtracting D, register D from register D, and then store the result back into, guess what, register D. So it is doing exactly the same thing as loading a 0 into register D. So it does the same thing. The difference is it uses 1 byte fewer compared to the LDI instruction, because LDI always uses 2 bytes and subdd only uses 1 byte. Yeah, I'm shaving a byte here in terms of optimizing the code. And then we have JMPI to main, because I want to maintain the ordering of the definition of the items in this program. So a variable is nothing more than a label followed by the number, a sequence of bytes. Okay, in this case it's only 1, because x is a unsigned 8-bit integer. It should only take up 1 byte in RAM. So this is how we make global variables. And then we have function f. A function is always identified by its name, a label of exactly the same name as the function itself. And in this case, let's start with the code to return to the caller first, and then we'll talk about how to return a specific value from the function. So to return to the caller, we assume the stack pointer, which is register D, is pointing to the return address right at that point. So we have a LD, not LDI, into a register B and then register D. So in this case, you can choose between register B or C, but not register A for a reason. I'll explain that later. And then after that, we have an increment D, because the location that was used to store the return address is now utilized, and we want to quote-unquote deallocate it so that location can be used again. So increment D is really just moving the bookmark that is separating which part of the stack is in use and which part of the stack is available. It's just moving that bookmark by one location, so that we now say, oh, okay, this location has now been utilized. It's not needed anymore, and we can use it in the future again. And then we have JMPB to utilize whatever value is in register B to continue execution from function f. So here's the mysterious part. Okay, the mystery part is, how do we return the value? Well, as it turns out, in TTPASM, in the way that I translate C code into assembly code, whatever you put into register A at the end of a function is the return value. It's as simple as that. Okay, you just say LDI A4. That's it. Okay, this is how you specify a return value of 4. So once again, this is an agreement between the caller and the callee that the callee would put the return value in register A. So by the time we get back to the caller will say, okay, what is the return value? Let me take a look at register A, because according to the agreement, the return value should be in register A when the called subroutine returns. Okay. Now, obviously, this is not going to work when you return a structure or return an object. Okay, but in this class, we're not going to deal with that. Okay, we are not going to deal with returning an entire structure, because it doesn't really happen very often in real life, and it is awfully inefficient regardless of how you implement it. So we are not going to touch that in this class. So now we're in main. We know the last instruction of main is going to be a halt instruction, because we want to stop the program from proceeding any further. And now we just have to remember how to call a function. So instead of doing the same thing as last time, I'm going to introduce a new way of specifying the return address. So we'll go ahead and do the usual stuff. Okay, we're going to put the return address into A, and I'm going to put some question marks here. Okay, how to specify the return address. And then the next line is to decrement the stack pointer to allocate 1 byte from the stack, and then stda to put our return address to the location that we have just reserved. And then followed by jmpi to the subroutine, which is f. And normally this is where the where f should return to. Okay. So now the question is, how do we specify these question marks? So as it turns out, there is a dot notation that in the assembly language. So what dot is representing is the address of the instruction on this line, the address of the first byte of the instruction of this line. So in this case, this dot is representing the address of the LDI opcode. So how is that going to help us? Well, it's going to help us because we can use the address of the LDI to calculate the address of the halt instruction, which is basically where we need to return to. So let's do some counting here. LDI itself is at an offset of 0 from itself. So offset 0 and offset 1 belong to the LDI instruction because LDI takes up 2 bytes. So the second byte of the LDI instruction is at offset 1 from the first byte of the LDI instruction. So we have 0, 1. This is 2 because decrement only takes up 1 byte. This is 3 because ST only takes up 1 byte. This is 4, 5 because JMPI-F takes up 2 bytes. So in the end, this halt instruction is 5 bytes away from the LDI instruction, which is 5 bytes away from the dot. Let me say that one more time. Let me just do the counting one more time. 0, 1, 2, 3, 4, 5. And this is at location 6. So I take it back. It's actually at the offset of 6, not 5. Okay, 6 bytes. So if we could do something like that, that would actually specify the correct return address. Dot plus 6. Okay. So I said if we could do something like this because this is an infix notation, which means the operator is between the values that it is supposed to operate on. The infix notation is great because we grow up with it, okay? But it's really not easy to parse because now you have to look at the operator priority because addition has a lower priority compared to multiplication and so on. So it's a mess if you want to write a parser for infix notation. So what I did was being lazy and use a postfix notation instead. A postfix notation is putting the operator after the value that it's supposed to be operating on. So dot 6 plus is accomplishing what normally would be expressed as dot plus 6. It's just that this is called a postfix notation where the operator is after the specification of the value that the operator is supposed to work on. All right, so that's the program. Okay, the nice thing about using this notation is we don't need the labels anymore. We don't need a label to say where f is supposed to return to. The problem of using labels is you can forgetting to define the label is not so much of a problem because the assembler would actually catch that. The problem is if you define the label but you forgot to change the reference to the label, so it's referencing an earlier label, then your program is not going to work correctly. And those are very difficult bugs to locate because your program is just going to go like, okay, it did the function correctly, but when it just returns to quote unquote la la land, right? And using this approach, makes sure that that does not happen. All right. So now we're gonna test this script and see whether it works or not. Because I made a copy. If you watched the video from this morning, I made a copy of the assembler, okay, and I also replicated the entire process that you will need to do in order to use the reverse spider tool. So we're gonna give it a try, give it a spin. So let's go ahead and exit from this. And let me see. Yep. Okay, River Spider is still here. And it's just ./submit.sh, and then the location of the TTPASM file. So it'll be in the parent folder, and it is return value .ttpasm. Press the enter key, and watch the magic happens. All right, it does work. This feels good. And then we go back to the spreadsheet. You can see this is the, oh, not this one over here. That's the copy of the assembler, not the original one. I made this just so that I can test whether the steps that I was taking was working or not. All right, so once we get here, we want to see if the program worked or not. It did work the way it's supposed to, and then I forgot one thing. We were not done yet, okay? I was a little bit too eager to test out this setup, but I wasn't done yet. I wasn't done. Okay, let me go back to the previous folder, and then so I can repeat the command like that. I wasn't done. I called the subroutine, but I didn't do a single thing about the return value. So we still have this part to take care of. In other words, we have to store the return value of f into the global variable x. So that is what I am going to do next in the assembly code. Okay. So after we return from the call to f, after f returns to main, register A is supposed to have the return value. Now we have to store that to local variable x. So to do that, we did this yesterday because we were working on a recursive subroutine that makes use of a global variable as a countdown counter. So we did this already. So we do a LDI. Now remember, don't destroy the value of register A because register A is the return value. So we're going to have to use register B or C. We cannot use register D because that's the stack pointer. You're not supposed to touch the stack pointer unless you're doing stack related operations. So we're going to use, let's use register C this time. So LDIC with X, which is the label. But the label is a symbolic name of whatever is next to it, unless you have an expression after X colon. Since X colon doesn't have anything after that, it is really the same as, okay. Now that we know the dot notation, X colon with nothing after is really the same thing as X colon dot, except, the syntax checker doesn't like that. So anyway, so right here we are loading C with the value of the label X. The value of label X is the address of the byte 0 location. So next thing is to do stca so that we store the return value, which is in register A, to where C is pointing to, but C is pointing to the location of global variable X. So that should finish the entire operation. And let's go ahead and exit Vim, go back to this subfolder, and then repeat the command. There we go. Now we can switch back to the assembler. So you can double check. You can double check the source is indeed the source code that we were dealing with. And you can also check a few other things. You can check assemble tab. This is how the program assembled. And the most important part is we now have to look at analysis. So the analysis is confirming that it does work because we are storing a value of 4 to location 4. Now that is completely coincidental, okay? It is just coincidental that the return value is exactly the same as the address of the global variable X. Now how do we know that it's just coincidental? We go back to the assemble tab, we look at the definition of X, and X is indeed at location 04. We also want to check the other two things, which is, did the program end with the halt instruction at location 13? So let's look at the analysis, and it did end at location 1, 3. That's good. And then one more thing to check is whether the stack pointer is balanced. It is supposed to end with 0, 0, and it did end with 0, 0. So this is how we can kind of check the program, make sure that everything is working. And in this case, specifically, we want to know whether the global variable x is getting the return value of function f. So any questions about this part? About the return value of a function? Okay. If there are no questions, we're going to move on. Okay. So let's make this program a little bit more complicated. I think we can do this. I think there's enough time to do this. The instruction in today's lab is going to also duplicate what I am about to say, so it's going to be okay. Even if I cannot finish in the lecture, the lab actually contains the instruction, but it's good to see me do it, actually here too. So let's go ahead, and I'm going to reuse the same program, except this time I'm going to make it slightly more complicated. So to make it slightly more complicated, I'm going to make f take on 2 parameters. So we're going to use u in 8 underscore tx and u in 8 underscore ty. And what it's going to return is the sum of those two. So it's going to return x plus y. And obviously, when we call f, we also have to supply some values. So we're going to say, okay, let's just add 3 and 4. This is C code. Pretty easy to understand, but how do we do this in assembly code? So the question is, how do we pass arguments from the caller to the callee? Passing arguments using registers is not a very good idea because we don't have a whole lot of registers, do we? We have register A, B, C, D. D is not usable anymore because that's the stack pointer. So we only got 3 general purpose registers left. And you can kind of imagine there are many, many functions that may take more than 3 arguments. So that's not a good idea. We can try to statically allocate a chunk of space in RAM and call that the communication area between the caller and the callee. That approach is actually used in many actual programming languages, particularly Fortran and COBOL both use that approach. But using that approach, we cannot do recursion, okay? Because there's only one static piece of area, so the recursive call requires each invocation to have its own area for its own arguments, so that's not going to fly. So the answer is, once again, the stack. Okay, so the stack is being used to pass arguments, and the agreement between the caller and the callee is the arguments have to be pushed first, and we also use the convention of the last argument is pushed before the is pushed first, which also means the first argument is pushed last. So in this example, 4 should be pushed before 3, and then we do exactly the same thing as we usually do, which is pushing the return address on the stack. So let's go ahead and do that. Okay, so we have 4, which is our first argument. And then I'm just going to be lazy and copy and paste. Oh, okay, I said copy, not delete. There we go. So this is pushing 4 on the stack, and also being lazy, this is pushing 3 on the stack. So we push 4, we push 3 on the stack, and then we push the return address on the stack, and then we continue execution at the subroutine. Alright, so that seems pretty easy. And the question is, inside the subroutine, how do we get to the arguments? Because when we get to function f, okay, so if I were to use a picture of what the stack looks like, at the highest location is the first item that was pushed on the stack. So that's going to be parameter y, and then parameter x is pushed, so it's below y, and then after that we have the return address pushed on the stack because that was the last item being pushed, which is also what register D is pointing to at this point. Okay, but we need to get back to x and we need to get back to y. But we cannot change D, okay, because there's a convention of, you cannot change register D to a higher location unless what D is already pointing to is no longer useful. But the return address is useful. We cannot just change that. So what are we going to do? Well, we can still do some calculations, right? So the approach is to do a CPR CD. So once I do this, then we would also have register C pointing to exactly the same place that register D is pointing to. But now we can do some calculations with register C because register C is not special in any way, so we can just utilize register C. So now we say, register C is pointing to some place that's close to what we need, which is parameter x. So we just have to increment C first. So by incrementing C, C now becomes the address of x, which means if we do LDAC at this point, register A is going to be the value of parameter x. And then if we increment C one more time and do a LDBC, this time register B is going to be the value of parameter y, because I just moved C to here first and then to here. So I'm just going to sequence this whole thing. This is initial. This is after the first increment. And this is after the second increment of C. So this way you can actually see a statically represented animation of where C, how C is changed. Now that we have register A being X, register B being Y, we just have to add those two. So we have add AB because we're adding B to A because register A is supposed to be the return value, remember? So by adding B to A, we do two things with one. We basically kill two birds with one stone. Because register B is Y, register A is X, we are actually performing the addition. But at the same time, we're also putting the sum into the right register for returning. So that's why it is kind of cool. And I think I deleted or moved one instruction in the wrong direction. There we go. Okay. So this is how we compute the return value, and this is the usual way of just returning, okay? Because register D has never changed. Register D is still pointing to the return address, so that's perfectly okay to reuse the code from before to return to the caller. So now getting back to the caller, okay? Getting back to the caller, and the caller is going to continue execution at this point. But now we got two additional things sitting on the stack. Not three, because the return address was popped from the subroutine. The subroutine, when they did the increment D, that is how the return address is quote-unquote gone. It's deallocated from the stack. But we still have the two arguments on the stack, sitting on the stack doing absolutely nothing at this point. Okay, they are not needed anymore because the invocation of the subroutine is done at this point. So what we do is we increment D twice to get rid of the arguments that are still sitting on the stack, but they are not needed to be there anymore. It is important to remember to deallocate your arguments because otherwise your stack is not going to be balanced. And having an unbalanced stack can be can be very bad. So that's the code, and we are going to test it. Okay, so I think we barely have. Oh, darn it, we are over time already. So I'm going to finish this, okay? I will finish this before we start the lab. It is return value dot ttpasm. And this time what we are looking for is storing a 7 into X. So when we go back to the assembler, we first go to the assemble tab, find out where X is. X is still at the same place because we haven't changed anything about the first portion of the program. So we are now looking for a value of 07 stored into location 04. And then when we go to the analysis tab, we are just going to look and go like, yep, got that. We also want to confirm that register D, the stack pointer, is balanced. Yep, got that. We also want to confirm the last opcode to execute at location 21 is our halt instruction. And we got that too. So that concludes the demonstration. So today's lab is pretty much about the same thing, and you will see duplicate explanation in the lab itself. So hopefully it's not going to be taking too long. And let me give you the passcode, and so we can start with that. All right. So tonight's lab is params and return value, which is exactly what we just talked about. So we go to edit. There is a passcode, and it is also frame. So the passcode of the lab is frame, same as the row taking word. And I will give you time to do this. So July 14th, and I'm going to give you the 3 extra minutes. So it's going to be 8:23 p.m. And I'm just going to copy and paste because Canvas is very picky about how I specify date and time. So there we go. We got the quiz or the lab going. I'm going to walk away for about 10 minutes, and then I'll be back to see if there are questions to answer. All right, I'm not seeing any additional text. I'm just going to check. Okay, so I'm not seeing any additional text in the text channel. I'm going to discontinue or stop